Hi everyone. Hello Discrete math students. So this is basically another little training or tutorial video in using Mathematica. And I want to concentrate on a couple of interesting little problems, fun little problems that we can solve using Mathematica. Sometime next week, I will post to Connect your first Mathematica assignment. If there's a problem and I cannot post it to Connect, I believe I can, but if there's a problem and I cannot post my own assignment to Connect, then rather than posting it to Connect, I'm simply going to email it to you directly from D2L. But before I use D2L, let me see if I can just put the assignment in Connect. I'm still sort of figuring out, exactly how Connect works. So, but I believe there's an easy way for me to submit my own personalized or customized assignments to Connect. So this is the world of online teaching, using all of this software, and I feel like I should get a degree in software engineering or something like that. And I'm sure you guys can relate. Okay, so let's get started. Mathematica is right over here. Okay, 1 second. Let me. Okay, hold on. And okay, I think I know what I'm doing here with this hide control panel. Okay, so let's say that I have an interesting problem, an infinite fraction. Something that looks like this. Okay, let me hope I'm doing this the right way. Okay, so 3, okay, plus, oh, sorry about that, 1 divided by, okay, 3 plus, okay, come on, why isn't this, come on, plus, this would be a lot faster if I was using a whiteboard or a chalkboard, so just please bear with me. 1 divided by 3, I don't know quite what happened over there, plus, that's supposed to be a 3, by the way. It looks like a 3 that's been struck by a bolt of lightning. That is supposed to be a 3. 1, I could make that 1 a little better. Okay, divided by 3, and then plus. Okay, and it just keeps going and going and going. This is an infinite fraction. It's an infinitely repeating fraction. I think you guys can see that. Excuse me. And yes, it's a wonky looking 3. It's a 3 that's been struck by a lightning bolt from the Greek god Zeus, but you can see it's a 3. So 3 plus 1 divided by 3 plus 1 divided by 3 plus 1 divided by 3 plus, and it just keeps going on forever and ever and ever, right? It's an infinitely repeating fraction. Okay, so let me, but you guys get the idea, I hope. Okay, let me clear that, and let me just I don't. Okay, okay? We can quit that application. Okay, so let's just focus. Let's focus on Mathematica. So let's see. So 3 plus 1 divided by 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 3 plus, oh my god, we're just going to go on forever and ever, right? 1 divided by 3, we could do another one for greater accuracy. 3 plus 1 divided by 3. Close all of our parentheses, shift enter. That's okay. In this case, I would prefer a floating point number. That's easy. 2 forward slashes in capital N. and that is about 3.302, etc., etc. I could also do this. Let me just copy and paste this. Copy, paste. Okay, apply the function using prefix notation. Okay, so the n function is great. Instead of the fraction 1/3, what if I want a floating point number? That's easy. Okay, you get the idea. Or I could do n 1/3, shift enter, very simple. You get the idea. Okay. But is there a better way to evaluate this fraction? So I know the answer is going to be approximately 3.302775. Okay, but is there maybe a better way to do this? Is there a better way to do this? And the answer is yes. I could use something called the fold function, okay? F-O-L-D, shift enter, and then I can read the documentation, either the local documentation or the online documentation, and this is going to give me all the information that I need to know about the fold function. It's a really interesting function. And for those of you who have done a lot of programming, like with C or C++ or Java or Python or Ruby, I'm sure you guys know all about for loops. In my opinion, this is similar to a for loop, but in some ways, it's actually much better than a for loop. Okay, so how am I going to use this? Well, let me erase that. Okay, first of all, fold normally takes 3 arguments. You can actually use it with 2 arguments, but I really prefer if you guys use it with 3. I think that's a safer bet. Okay, so your first argument has to be a function of 2 variables. So I'm going to create a function here, and there are several different ways in Mathematica that you can do this, but there are several different ways that we can do this in Mathematica, but this is one option for creating a function as an argument to another function. So this must be a function of 2 variables, by the way. Not 1 variable, not 3, not 4. It must be a function of 2 variables. So my first variable, I mean, you can use any letters you want, A and B or C and D or, X and Y, whatever you want. But in this case, I would like to use the word accumulator. Because, excuse me, I was yawning. Just a little tired today. Okay, so my first variable is the accumulator, which for this problem is actually the ever-increasing denominator of my infinitely big fraction. That's going to be my accumulator. And your second variable, I don't know, you can call it, num, if you want to call it that. Now, normally, yes, guys, you would use underscores, right? But in this case, we don't need to use underscores, okay? Because we're using the keyword function, okay? So here, what we're going to do is, and by the way, I didn't do the highlighting or changing this to the color red. That was done automatically for me by the Mathematica program, which indicates that my syntax is correct. So for this, what should I do? Okay, well, that's easy. That's going to be num plus 1 divided by my accumulator. Okay, and my function. My initial accumulator is simply going to be 3, because remember, it's 3 plus, 1 divided by 3 plus 1 divided by 3 plus, etc., etc. It goes on and on and on for as long as you want. Okay, here we don't need that part right there. And then I need a whole list of 3's. So my initial accumulator is going to be this 3. And then the num value is going to be all the numbers inside my list. And how would I do that? Constant array 310. So I have 10 threes. So what I could do is constant array 3, and this is going to be some variable. What should I call it? Oh, I don't know. I'm going to call it, how about x? And my function, I'll call it infinite fraction. It's a function of the variable x. And here we go. Okay, so that looks good, right? So let's see what I get. Infinite fraction. What if x is equal to 0? What do I get? Oh, you know, by the way, I should really change this into. I should really change. I want floating point numbers. So you know what? Instead of 3, I'm going to use 3.0. I think that might be a little bit smarter. So let me shift enter again. Okay, so infinite fraction 0. Okay, terrific. Infinite fraction. Okay, now I know how to spell. Infinite fraction 1. Okay, is that true? Let's see. 3 plus 1 divided by 3. Okay. And what about infinite fraction 2? Okay, is that true? So 3 plus 1 divided by 3 plus 1 divided by 3. Okay, and then let's try infinite fraction 3. Okay, let's try that now. 3 plus 1 divided by 3 plus 1 divided by, wait, 1 second. 3 plus 1 divided by 3. There we go. And then let's just do one more. So infinite fraction 4. Oh, yeah, we could do 4. Okay, oops, sorry about that. Okay, so a lot of parentheses, right? 1 divided by 3 plus 1 divided by 3 plus 1 divided by 3. 3 plus 1 divided by 3. There we go. Okay. Obviously, you really don't want to spend your whole day typing parentheses, right? Opening and closing parentheses. That's going to get a little bit confusing. So it makes more sense to let a computer program do that for you. So let's see. Does this converge? I believe it does converge. Actually, as far as I know, all of these infinite fractions really do converge. So let's see. My table, infinite fraction. I'm going to make up a letter. I like the letter K. Use any letter you prefer. K goes from 0 to 200. Okay, and what do we have? Okay, it looks very convergent to me. So when I say convergent, what that means is as the list progresses toward the end, you can see that the numbers don't really change that much. Okay, so you see that there is convergence going on. All right, and let me see here. So what would be a good way to do this? So my table form. Okay, so we start with, excuse me, we start with 3.3333, and 3.3, and blah, blah, blah. So you guys can read this for yourselves. I don't have to read every digit to you, I hope. And you can see that after a while, you know, the numbers don't change at all. So they zero in on the value of about 3.302775637732. Okay, so we see that the convergence here is really excellent, right? You can see that we have fantastic convergence going on here. Now, if you didn't have convergence, the numbers would not be the same. They would be scattered all over the place. You would have 3 point something, followed by 1,000, followed by 100, and followed by negative, 50,000. The numbers would be scattered all over the place. But you can see, excuse me, you can see that um, as the number of iterations increases, okay, the difference between successive values becomes less and less and less and less until finally there's no change at all. And we can see very good convergence going on here. So we know that the value is approximately 3.302 775637732. Now, in this particular case, it is possible to get a closed form solution to the problem. The drawing tool that I have is really not, sensational. Um, I could draw this out for you, but this is going to be a little bit difficult. It might be easier if I explain it in an email, perhaps. But a problem like this actually can be solved analytically, believe it or not, using simply the quadratic formula from high school algebra. But the point is, there are many problems in math and science and engineering where the closed form solution is extremely difficult to get or maybe doesn't even exist as far as we know. In which case, we need an algorithm that we can use to find an approximate solution. I'm going to give this a whirl. I hope this doesn't totally turn into a disaster, but let's see if I can use my drawing tool, and let's see if we can try to figure out the closed form or analytical solution to this problem. All right, so bear with me. Okay. Okay, let me see. Draw on my screen. Okay. And we can hide the control panel. Okay, hope this works. And okay, so let's say that we have the expression, oops, what am I doing? Okay, here we go, 3. Okay, I wish this would draw a little bit faster. It's the cursor is really lagging behind badly. Plus, okay, and then we're going to have 1. Okay, and then we have 3. Okay, plus, yeah, the drawing tool is really kind of slow. I could write this a lot faster with chalk or a marker, but just bear with me, please. And then we have 1, divided by 3, okay, plus, you get the idea, and it just, it keeps going on and on. Okay, so we're going to call this L. L means limit. If you ever had calculus, you're going to understand why I like the letter L, capital L, okay? So L is equal to, okay, L is equal to 3 plus 1 divided by 3 plus 1 divided by 3 plus etc., etc. However, bear in mind that this is an infinite fraction, which means that this whole thing right here is also going to be L. Okay, does that make sense? So what I really have, hold on one second. What I really have then is L is equal to 3, okay, plus, okay, 1 second, 1 over L. Okay, I have L is equal to 3 plus 1 over L. I better write that down just in case I get stressed out and forget it. So I have L is equal to 3 plus 1 over L. Okay, so let me, hold on 1 second, let me quit that application. If you're not using an app on your computer, it's probably a good idea to close it because otherwise you are using a lot of background memory, and that's not recommended unless you have a huge amount of RAM on your computer. you know okay, so we can actually use the quadratic formula in this case, but in this case let's not worry about it. I'm just going to use Mathematica's solve command. Okay, so I have solve. First, I have to make sure, hold on 1 second, clear L. Okay, just to make sure there isn't any value that I stored in L. Okay, if I do this, L is equal to 2, okay, then what I'm about to show you is really not going to work. Okay, let's clear L. Okay, solve. L is equal to 3 plus 1 divided by L, and the variable that I'm solving for is L. And yes, you can use the quadratic formula to figure this out. Okay, so we have two values here, 1/2 times 3 minus the square root of 13. We have one, and we also have 1/2 times 3 plus the square root of 13. Now, here's the deal. Because I realize there are two solutions to this problem, however, really there's only one solution, because if you looked at the original sequence, if you looked at the original sequence that defined our infinite fraction, you only had +1 and +3. There were no negative values. Therefore, we can ignore the negative solution to the problem. The only solution that we're interested in is the positive solution. We only want the positive solution, which happens to be the second solution, 1/2 times 3 plus square root of 13. Okay, so let's see. Is that really the answer? 1/2 times 3 plus the square root of 13. Let's turn it into a floating point number or a floating point approximation. Well, what do you know? That really is the answer to the problem. That really is the answer to the problem. It is 1/2 times 3 plus the square root of 13. Now, here's the point that's really important for you guys to understand, especially if you continue to study math, okay? This is called the analytic solution or the closed form solution. It's the real answer to the problem. Okay, this over here, okay, or I could highlight this value, that is the approximate solution. Okay, it is not the analytic solution, it is the approximate solution. The important thing to remember is that for many applications, like if you're an engineer, for example, if you're an engineer, you're probably not going to be interested in this answer. You're going to want this answer. And there are many math problems that are so difficult and so complicated that you will never be able to find the analytic solution anyway, in which case you have to settle for a numeric approximation. And that's really an important point, not only in discrete math, but really in any branch of mathematics that you decide to study. Okay? I think we have done here. Let's review what we've done because it's almost time to quit. Okay. Um, you really should understand how to use the fold function. I realize it looks kind of complicated, guys. It's really not that terrible. I strongly encourage you to do some reading about the fold function. It's actually an alternative to traditional recursion. It really is in many ways the same as recursion. It's a different form of recursion. That's really all it is. I introduced you to the constant array command or function. You should know how to use capital N, okay? All Mathematica commands begin with a capital letter. The capital N function, the N function, the N command. Um, we talked about infinitely repeating fractions. We talked about folds. We talked about convergence. Convergence is a very important concept. Um, and let me see here. You have an idea of how to use the solve command. Now, by the way, if I were to do something like this, L is equal to 2. Okay, L is equal to 2. Do you think that my solve command is going to work? No. And you know what it says? 2 is not a valid variable. So I have to clear L. I cannot emphasize that enough. Clear L. And now the solve function, the solve command works just beautifully. Okay, I hope that this was helpful to you. And I guess that's it for now. Take care and goodbye.